Si em permeteu, I would like to introduce Dr. Corinne Legal-Lassalle. I'm sorry, but I haven't practiced the pronunciation. She's professor at the hydrogeochemistry at the University of Nimes, and her research is on the origin of water bodies and their quality, with a special interest on pollutants from human and agricultural origin. She's part of the research unit GROM, the emphasis of which is to study the response of population and ecosystems to a perturbation in view to maintain the quality of life. So thank you very much, Corinne, and the floor is yours. Pots mirar això? Si
Is that, yeah, that's fine. I found the button. Okay, thank you very much. Good afternoon, everyone. I'm very pleased to be here with you today. And thank you, Professor Maspla, for inviting me so we can celebrate together the World Water Day. So as was said, I will talk to you about the occurrence of pesticides and emerging contaminants, specifically pharmaceutical contaminants that we can find in groundwater bodies. So I'm Professor Corinne Legal-Lassalle. I'm from the University of Nîmes, and the research unit I'm from is a very transdisciplinary research unit, and we study objects from all the point of view, from science, hard science, as said, up to the law and the psychological point of view. So we look really at all the angles of the same problem. So, keep that one. No. That one. Well, there's animation, so I have to click every so often. Hang on. Did you pass that one? Yeah. Okay, so here we are here today to celebrate the World Water Day, and this year is specifically talking to us because it's groundwater, and groundwater is invisible. It's held in the interstices of soil. Can you hear me? That's okay. Yeah. And thank you. The UN motto this year is groundwater may be out of sight, but it must not be out of mind, and that's what we're going to talk today. Oh, all gone. Hang on. It's fine. Okay, so just to remind us how important groundwater is. So, yeah, that's fine. You know that the biggest reservoir on Earth is the ocean, and it's saline water. And just to remind us, fresh water is only 2.5% of the total of the amount of water on Earth. 70% of that fresh water is trapped in ice caps and snow. And what is left is about 30%, 31% of the water, of which only 3% is on the surface of the Earth, and the remaining bit is groundwater. So that's about all of the available water, fresh water, to human being. So it is a very important reservoir. Hang on. Just to remind us as well, the sustainable goals defined by the UN. So groundwater will be of the utmost importance for the sixth sustainable goal, with distribution of clean water and access to sanitation. But not only for that one, it's also very important for the number 14, life below water, and life on land. Obviously, water is important. But not only for those three, there's also that one, number 2, which is very important. If you don't have water, you don't have irrigation, and you cannot irrigate crops. So this is also very important. So water is of the utmost importance, and groundwater is as well. Just to remind us, those were numbers. 3 out of 10 people do not have access to safe drinking water. And that's for women. Raise the hands, women. Quite a few women here today. Access to water is very often linked to landowners, and women are not land tenures, so only 20% of women are landholders. So that restricts the access to water to women. Okay. So let's get started with the study we did for a joint joint program initiative at the European level, where we looked at the fate and the persistence of emerging contaminants and microbial resistant bacteria in surface water and groundwater, in a continuum from the groundwater scale to the laboratory scale. The project was held by a consortium made of CROM, ICRA, and the Helmholtz-Zentrum in München. I'm going to talk to you mainly about the groundwater part of that study that we carried out in the field near Nîmes, so not very far from Girona. So what we were looking at is at the field level. So here you've got a cross-section of an alluvial aquifer, something very simple, where you have here the water table is symbolized here by that line. And you have the stream, you have canalized water, you have the township, you have household, you've got agriculture. So you have all sorts of land usage on the top of the basin. And what we will be interested in is what is the fate of the contaminants that are produced at the surface by wastewater treatment plant, coming from septic tanks or through agricultural usage in the groundwater. So how does it, well, is it going from those sources to the groundwater and to the borehole where the water is abstracted? So we have, so if we look at the question in the small water cycle, so you've got the water supply here, symbolized by that water castle. It is used, and it goes out of the household through used water. It goes into the wastewater treatment plant. And from the wastewater treatment plant, it just goes into the streams, the nearby streams. And from the streams, it is possible that it goes back to the groundwater. And then you have closed the cycle, Then you have closed the cycle. The question is, if you take medicines, if you take drugs, you're not going to metabolize all the molecules, and those molecules will end up in the wastewater treatment plant, and then into the environment. we splitted the work. Oh, so we looked at 24. We looked at 24 molecules, including molecules like carbamazepine, oxazepam, which are antiepileptics, diclofenac, which is un décontractant. You use diclofenac? Voltaren? Yeah. And antibiotics such as oxythromycin, ofloxacin, sulfamethoxazole, and the third generation antibiotics, ciprofloxacin and cepflaxin, which are of very important interest in terms of resistant bacteria. So, we looked at the Vistrak aquifer here. Nîmes is around here. For those who know the south of France, the Rhône River is going around here. And that aquifer is made of an alluvial deposit, which was deposited by an ancient Rhône riverbed. So the Rhône was going through the plain in the past and deposited all the alluvions here. And this is the aquifer that we're looking at. It's mainly unconfined, but sometimes confined below quaternary deposits. It's relatively big at the regional scale, 350 square kilometer, and it supplies water for about 200,000 inhabitants. It is used mainly for water supply, for drinking water supply, but it also supports the industry, agriculture, and some private wells as well. So it's a fairly used resource, as there is no other water resource in that plain. Okay, the land use, so 80% of the basin is used for agriculture. So you've got in green vineyards and orchards, and in white here all the other agricultural practices. In pink you have urbanized areas, so Nîmes is around here, and you've got several villages that are all around the plain. What is important as well on that slide is those purple dots, which are all wastewater treatment plants from all those villages. So there are 20 wastewater treatment plants on the plain. And all those water treatment plants produce wastewater, treated wastewater, that goes into the stream. If you don't live in those urbanized areas, then you will live with a septic tank, and the septic tank will directly leak into the aquifer. So the first task was to look at the quality of the surface water. So we looked at what kind of molecules we could find in the stream. We have to realize that in summer, the water that flows in the stream is 95% effluent from treated wastewater treatment plants. So the occurrence of molecules is quite important. So we would be looking at, oh, hang on, it's all messed up here. We would be looking at the evolution of the concentration of emerging contaminants along the streams from the spring to the mouth. And this is what we found in the first survey. So here you've got the 24 molecules we've been looking at, and the concentration in nanograms per liter. And here we've got a log scale. So we have things like sotalol, what did we talk about? Oxazepam here, carbamazepine, where is sulfamethoxazole, in the order of hundreds of nanograms per liter. Could you remind me of the limit for, or the guidelines for pesticides in drinking water? Who knows? What is the guideline? Joseph? No? 1,000 nanograms per liter. Okay, so this is not for pharmaceuticals guidelines, but it's just to give you the scale. So those concentrations are relatively high, and that's in the natural environment. So we looked at, to make sure that those concentrations are coming from the wastewater treatment plant, we looked at the concentration in the wastewater, in the effluent of the wastewater treatment plant, and the concentration in the streams in blue. And we can see that after the point where the effluent is going into the streams, then right after that we have a peak of concentration in the spring. So that is a sign that, yes, those molecules are coming from the wastewater treatment plant into the environment. Here we've got, again, carbamazepine, macrolides, sulfamethoxazole, and some fluoroquinolone here. So dilution is important as well, but still we maintain quite high levels of molecules here, as we've got like 30 nanograms per liter of carbamazepine. So we used to say that the fishes are very, very cool in that stream. We also looked at the evolution of the concentration of the molecules along time. And here, so we still have the concentration in nanograms per liter. We've shown here carbamazepine and some antibiotics, cephalexin and erythromycin. And what we can see is here, for example, for cephalexin, we can see a peak, and that's most likely linked to a period where those compounds have been prescribed in end of winter. So the concentration depends on the prescriptions. For carbamazepine, which is a medication that you take every day, so that will have a continuous input in the wastewater treatment plant. And the variations of those concentrations are probably mainly due to dilution and the amount of water in the stream. And here we can see, as a matter of fact, that as the level of water increase in the stream, you have the concentration of whichever contaminants you're looking at, so those which are quantified in sufficiently important concentration, they decrease with the increasing height of water. So, having said that, we have those molecules in the stream in quite significant concentrations. We cannot say it's high concentration, but it is significant. Nanogram per liter, how much is that? Well, if we look at the prescription, let's say paracetamol, which you take about 1,000 milligrams in one pill. You take a tenth or hundredth of that pill, so tenth of a hundred, very small, and you put that in a Olympic swimming pool. Okay, this is about what is a nanogram per liter. So it's very, very small concentrations. Nevertheless, it's there. So the conclusion, we looked at 24 molecules and we found 24 molecules. The input is from the wastewater treatment plant effluent. Some of the molecules depend on the prescriptions. and it is diluted by high flow rate. So now let's have a look at the second task. We focused on what happens in the groundwater. Mainly when you think about groundwater, what do you think about? You think about spring, and if you think about spring, you think about clean water, right? So groundwater, hopefully, should be clean without any contaminants. This is what we're going to look at. So we looked at all those dots, which are boreholes that we sampled along the plain. So we sampled 50 of them. We looked for 24, not 34, 24 pharmaceuticals. And what we found was concentration. So those are total concentrations of pharmaceuticals in those bores, and they range from below the detection or the quantification limit up to that one here. So it's outside of our area, but nevertheless, up to 100, above 100 nanograms per liter. So in places where we would have thought should not be impacted by those molecules, we can find pharmaceuticals. So 27 of them had a concentration between 1 and 50 nanograms per liter, and 5 above 50 nanograms per liter. So some of those bores, you have significant concentrations, and you're sort of in the middle of nowhere. The question is, where does it come from? The others, you may be closer to the source, closer to a stream. So if you're close to a stream, maybe then the stream is the source of the contaminants. So what we found in those groundwaters was carbamazepine. So you will see that this is a very persistent contaminant that is not degraded in the environment. So it's a very good tracer of the pathways for contamination. You have ofloxacin as well, sulfamethoxazole that we could find as well. So we found 13. We found 13 quantified pharmaceuticals in the groundwater. Then we wanted to focus on those wells where you found higher concentrations, and those wells ended up being not very far from the streams. So we focused on those clusters with a well close to the streams, and we followed the concentration a long time. And that is the task number 3. That's what we've been looking at, is the relationship between surface water and groundwater. And to start with, as geochemists, we want to make sure that the signature of the groundwater confirms that it may be impacted by water from the wastewater treatment plant. So we look at the signature, the geochemical signature of the water. And that's what we've done here on principal component analysis. You know what principal component analysis is? Yes, some of you, all of you. Well, so on the principal component analysis, we can see that we have here the wastewater treatment plant, which is a sample here, which is in agreement with high concentration of emerging organic contaminants. So that works well. So it comes along with chloride and sodium and potassium, which are markers of the wastewater treatment, of the wastewater effluents. On the other side here, we can see another marker, which is deuterium, which is the marked signal for water. And we see that it is fairly independent from AUC. So we've got two independent traces here, and that will be useful for us. We'll see that a bit later. So, okay, we have the groundwater samples here, and some of them are going toward the wastewater treatment plant. In those clusters, we look at the surface water and the groundwater together. And what we can see here for some concentration of emerging contaminants here, we can see that the signal of the surface water is followed by the signal in the groundwater quite clearly. So here we can also confirm that the surface water goes directly into the wells. And then we looked at the deuterium, so that tracer we looked at here. So we know there's two different traces, independent traces, but in the stream it happened that the signal of deuterium here and carbamazepine here follows the same pattern. So we can trace the origin of carbamazepine with deuterium. And that's what we've done in the groundwater. If you plot carbamazepine against deuterium, we can see that it is following a line which shows that the carbamazepine and deuteriums come from the same origin and confirms the origin from surface water. So we're happy with that. Well, happy, sort of. And this is what we found in those clusters. So we looked at the occurrence of those molecules, and here we found all the 24 molecules in those clusters, which shows that compared with the rest of the groundwater survey, we have more molecules. We found more molecules in those clusters. If we look at the frequency of detection, or frequency of quantification in the groundwater survey, which means at the scale of the resource, compare with the quantification frequency in the clusters. This is the line 1-to-1, which is the same occurrence of the molecule in the groundwater survey or in the clusters. And we can see that most of the molecules are well above the line of 1-to-1, which shows that in those clusters you have more molecules than in the rest of the groundwater body. And if we looked at the concentration in the groundwater survey, so at the scale of the groundwater body and at the scale of the clusters, this is again the line 1-to-1. We can see that for some of the molecules, we have more higher concentrations. So if you want to buy a house, where would you buy a house? You don't know. Not or at least not close to the stream with a borehole. So 24 quantified molecules increase frequency of quantification in relation to the proximity of contaminated surface water, and increase concentration in the vicinity of the contaminated surface water as well. So what would be interesting to look at is whether those molecules are attenuated from the stream to the borehole. So this is the next slide. We look at the attenuation. We looked here at the quantification frequency in surface water and in the clusters, so in the well that is close to the stream. Again, this is the line 1-to-1. And we can see that the frequency of quantification in the clusters, in the well next to the G, is lower, mostly, than the one line 1-to-1. So we have less occurrence of those contaminants, but still they go through. So here the line 1 to 1, the line 1 to 2, and the line 1 to 8. So it goes up to a eighth of the frequency in the stream. And with respect to concentrations, we have the same things. Sorry, up. We looked at the concentration in the surface water, and here the concentration of the groundwater. We have the line 1 to 1, and the line 1 to 10, and probably 1 to 20, that one. And we can see that some of the molecules are on the line 1 to 1, which means that it is the same concentration in the surface water and in the well. So those molecules like carbamazepine and ibuprofen are not attenuated as they go through the sediments of the alluvial aquifer. If we look at sulfamethoxazole, which is around here, so it is slightly attenuated, but it is still there. So, to conclude on that, most of the molecules show an occurrence divided by 2 to 8. So this is 2 to 8 here. There are no decay for some of the molecules, carbamazepine, sulfamethoxazole, or ketoprofen, in terms of frequencies. Most of the molecules are attenuated by a factor of 2 to 30, but carbamazepine, ibuprofen, and flumecine. So in conclusion of that, in the groundwater survey, we quantified 13 molecules. The concentration of the pharmaceuticals in terms of concentrations are from a few to 100 nanograms per liter. So I remind you, it's like a tenth or a hundredth of pills in an Olympic swimming pool. It's originates from surface water, and we also look at the microbial resistance, but I didn't have much time to talk about it, and it's really, really far from my area of expertise, so I apologize for that. And in the clusters, we found 24 molecules. There are evidence for persistence of molecules that goes with little and no attenuation. There is an attenuation for most of the molecules, but still they go through and they end up in the wells. And the decrease in and there is a decrease in the frequency of the occurrence from surface water to groundwater from 1 to 8. And here we sort of summarized the dilution sort of or attenuation rate if you go from the drugs to the wastewater treatment plant, to the streams, to the groundwater. So sort of you divide from the drugs to the wastewater treatment by 200,000. Then from the wastewater treatment plant to the streams by about a factor of 10. And then from the stream to the groundwater by a factor of 1 for some, which are not degraded at all, to 10 or 100 for the rest of them. So this is the life of the pharmaceuticals, our pharmaceuticals. So if next time you take a pill, you think about what's going to happen to that pill. And for those of you who are chemists, what is important to think about is to make drugs that are degradable, to improve the wastewater treatment plant to prevent molecules to enter the natural environment. And maybe the fish will be a bit more nervous next time. So thank you very much. I think I'm about right on time. Otherwise, I've got another 10 slides to show you, but no, we'll stop there. Thank you very much. time for questions, if you have any questions.
Thank you, Corinne. Thank you very much. Yeah, it's time for questions. Yeah, maybe may someone.
This one there. Maybe I can repeat the question if you want. What we can do at the scale of the wastewater treatment plant, is that the question? Yes. Yes, most probably. There's still yeah. The question is if we have tertiary treatment, if we implement tertiary treatment in wastewater treatment plant, can we solve the problem? Yes, most probably. The question is how far we go for that treatment, further treatment, and how much it's going to cost. The question is how much you're happy to pay for that treatment, because I don't know how it works in Spain, but in France we pay if you use water, when you pay the bill, you pay the treatment. So the question is how high are you happy to pay your bill to clean the water before it goes into the environment? Yes, there are solutions that could be implemented, like what? Where are the chemists? Membranes? Ventilation, microbial activity, maybe, but some of the problem with the antibiotics, that they are hardly degradable because their job is to kill microbes. Charcoals, filtration. So all those techniques are studied to try to decrease the level of concentration of those molecules. There are pilot plants that are looking into that. Well, the question is how much you're ready to pay for. Yeah, I had a question.
Yeah, sorry. My question's kind of connected, really, because I was just thinking, I'm from Wales, where it rains a lot, and I was just thinking about what happens in countries where there's no treatment at all. Because we're talking about treatment, you're talking about places like France with highly sophisticated water treatment, sewage treatment systems. But what happens in other countries? What happens in third world countries, for example? Are you running systematic partnership projects with other countries to find out the levels there? Because this is stuff that, from my very basic understanding, has already been treated to a certain extent and filtered. But what are the levels? Do you have any data of the kind of shocking, horrible levels of what it's like if it's not treated at all?
No, I don't have data, but obviously there's one thing that we have to understand is the wastewater treatment plant currently, the aim is not to degrade those molecules.
No.
That it's not their job. But they do a good job at that. Now, if you don't have those wastewater treatment plants, the question is, what is the pressure of pharmaceuticals? It goes maybe together. Well, is the consumption of pharmaceutical high or not? If it's not too high, then maybe it's not too bad. But yeah, I don't have any numbers. Yeah. Yeah, probably there are more other problems that are more important, like bacteriological problems and so on, that the pharmaceuticals at that level, I would say.
Hello, Corinne. Thanks for the talk. I just wanted to highlight two things. One, the way you have explained it, the hydrological cycle, which is indeed the framework where all these pollution problems must be understood somehow, no? And the other thing is that when you show the part of the PCA with all these chemicals, sulfate, calcium, sodium, I mean, you're talking about that the pesticides, or in this case, antibiotics or pharmaceutical products, they move around the aquifer because there's a conveyor, and it is groundwater. Yeah. And groundwater is the transport media that uses, and the occurrence of an antibiotic in a well, in a spring, anywhere, it's because of these hydrological dynamics. It's not there just because it's there. It's because someone, I mean, groundwater has put it there, following some hydraulic rules, in porous media, I mean, in several hydrological systems at different scales. Anyway, I wanted to highlight this because it's a Groundwater Day and so on, and this is a very important part of your talk. And I know here most of the people are from chemical engineering, so it's worth recalling that the environment is very complex. But my question is something I think I know the answer, but why should we worry about a few nanograms of liter of any of these pharmaceutical products? That means nothing in an Olympic swimming pool. What should we worry about that?
Good question.
I'm sorry.
What do you think? Well, the beginning of an answer to that question is the comparison with the guidelines for pesticides. Okay, we're not very far off. What is another answer? We looked at 24 molecules. Okay. How many chemicals can we produce? Hundreds of thousands. I mean, there are all sorts of molecules that you can find in, and one of the question, where is it? One of the question is the cocktail effect, which is if you add all those molecules together, what is the concentration of that cocktail and what is the effect of that cocktail? So for pesticides, 100 nanograms per liter is the guideline for one compound, and for the sum of all the compounds is 500 nanograms per liter. So you cannot go above that limit for the sum of all the compounds. So the cocktail is the question. Is that what you were thinking about? Yeah. So anything you're doing with water, think about the impact and the imprint you have on the environment. Yep.
I'm not sure if it's beyond the research scope, but is there any data on the concentrations on the tap water? And is it possible that the contaminants keep cycling in the system?
Yes. I don't want to have enemies, but obviously if it's in the wells, then it can be in the tap water. Tap water is not necessarily filtered. It's just disinfected often, and that's usually enough to make it drinkable. So there's no reason why it shouldn't go up to the tap water. That wasn't in the scope of that research. No. But I have a student who wants to do that. Look at the tap water. But there is no filtration, there is no guidelines, currently it's not monitored. So it's a good question.
Okay, so thank you very much, Corinne. Thank you for the audience for these interesting questions.
Thank you
A big
very
applause
much.
for you.
Thank you.